In today's lecture, we will see that if a system, LTI system is not controllable, then can we find a state vector, state space representation where the state vector can be divided into two parts. The first part being known as the controllable state, and the second part known as the uncontrollable state. So for this, we'll again consider our LTI system. We'll only focus on the state equations and not on the output equation, since the controllability is related only to the matrices AB. Okay. So A and B are constant matrices. This is an nth order system. There are m inputs to this system, and A and B are constant real matrices of appropriate dimension. Now suppose this AB pair or the LTI system that we are considering is not controllable. That indicates that the rank of QC is going to be less than n. Okay, and the rank of QC will be equal to, let us assume that it is small q, which indicates that in this controllability matrix QC, you will have n number of linearly independent columns. Okay, because the rank of the matrix QC is q, small q, so there would be small q number of linearly independent columns in this QC. Now what we want is to find that state vector and represent it with, find a state space representation with this special state vector, so that this state vector has these two parts of controllable states and uncontrollable states. So for this, we need to transform this given state space representation to a new state space. For this, we need to find the suitable transformation matrix. So we construct a matrix. Okay, so let us construct a matrix P, where the first q columns are the q linearly independent columns from QC. So essentially QC has n into m number of columns, so nm number of columns. From this nm number of columns, choose q columns which are linearly independent. Pick those columns and use them to form the first q columns of the matrix P. We'll label them as P1 till PQ. Now we remain with n minus q number of columns to be filled up for the matrix P. This n minus q number of columns are your choice, but you have to ensure that when you fill up this n minus q number of columns with the vectors pq plus 1 till pn, the entire matrix P is invertible, which means all the n columns that you have in the P matrix have to be linearly independent. Okay, so that is how this P matrix is constructed. Your first q columns are the linearly independent columns from the controllability matrix. The remaining n minus q columns are chosen such that the entire P matrix is invertible. So the rank of P has to be n. Now suppose you have a state vector Z, which is related to x through the relationship that Z is equal to P inverse x. Now the system that I have here, I have given the entire system here, x dot equal to ax plus bu and y equal to cx plus du, can be represented using this particular new state vector Z as this. So Z dot is P inverse APZ plus P inverse BU, and y equal to CPZ plus du. Okay, so this is how it can be found. Now this P inverse AP and P inverse B have a very special structure associated with them. Okay, but before we go there, the Z is going to have this structure. So the ZC transpose will be of the size RQ, and ZC will be RQ and ZC bar will be Rn minus Q, where ZC is the controllable states and ZC bar is the uncontrollable state. Okay. Now we want to understand that what is that special structure that is there associated with P inverse AP and P inverse B because of such a peculiar choice of the transformation matrix P. We will first see what is the structure of P inverse B. So let's say that P inverse B is equal to some matrix G. Okay, so some matrix, some representation, which indicates that B, the matrix B from the original state space representation is nothing but P multiplied with G. Okay, now P is what? P is P1 till PQ, PQ plus 1 till Pn. So this is the n number of columns that you have got in P multiplied with the matrix G. So what this indicates that each column of B is a vector arising out of the linear combination of P1 till Pn. Okay, and the coefficients associated with the linear combination are corresponding to the entries in the column of G. So the first column of B is a linear combination of P1 till Pn, where the scalars associated in the linear combination are coming from the first column of G. Okay, that is how the structure is. Now note that the columns of B are essentially the columns of the controllability matrix QC, because this is by construction, which means that each column of B can be represented as a linear combination of the Q number of linearly independent columns in QC, which in our case we have chosen it to be P1 till PQ. So the coefficients associated with PQ plus 1 till Pn, so as to represent the column of B, have to be 0. Okay, hence what happens is G will have all its columns such that the first Q entries will have some value which is not necessarily 0, but the remaining n minus q, the last n minus q entries in each column of the G matrix would be 0. Okay, so hence the structure of G is BC, which is some matrix, and 0. The size of this BC is going to be Q cross M. So P inverse B has this structure. It has a block which we'll label as BC, C indicating controllable, and a 0 block. Now what happens to the P inverse AP structure? So to analyze the P inverse AP structure, let us say that it is equal to some matrix F, which essentially means PF is going to be equal to AP, and AP is nothing but A acting on P1, P2, P3 till Pn. Okay. Now notice that A, when acts on QC, where QC is the controllability matrix, is nothing but AB A square B till ANB, where AN can be expressed as a linear combination of A power 0, A power 1 till A power n minus 1. I'm sorry, there is a coefficient alpha missing. I'll correct that in the notes. Okay, so that is how AN can be represented, which means what? That since the columns of QC can be expressed as a linear combination of P1 till PQ, so the columns of AQC can also be expressed as a linear combination of P1 till PQ. Okay, this essentially indicates that when A acts on P1, then it results in a vector which can be expressed only as a linear combination of P1 till PQ, whereas the components associated with PQ plus 1 till Pn would be 0. This holds for vectors from P1 till PQ. Okay, so if we proceed further, every column of AQC can be expressed as a linear combination of P1 till PQ, Thus, AP1 till APQ can be expressed as a linear combination of P1 till PQ. AP1 as a linear combination of P1 till PQ. AP2 can also be expressed as a linear combination of P1 till PQ, and so on till APQ. Okay. So from this, what we get is the first Q columns of the matrix F will be such that the last n minus q entries will be 0. And hence F has this nice structure of AC, A1, 0, A2, where AC is a real Q cross Q matrix. It is worth noting that the pair AB is not controllable, but after this representation in the state vector Z, the pair ACBC is controllable. And this is what will be used to establish the concept of something known as stabilizability of a system. Okay, so what we did here is also known as the controllable canonical decomposition of a LTI system. So what we did was we found a state space representation where the system can be broken into two parts, the controllable part and the uncontrollable part. So if you observe from the structure of F and G, or the structure of P inverse AP and P inverse B, ZC transpose, the derivative of ZC bar, okay, sorry, not ZC transpose, the derivative of ZC bar is equal to A2 multiplied by ZC bar. There is no effect of input U that will come in ZC bar evolution, okay, and hence the ZC bar matrix is said to be uncontrollable, or the ZC bar state is said to be uncontrollable. There is no effect of U, no matter what you design on ZC bar. Okay, so we will stop here and continue our discussion further in the next lecture. Thank you.